that a good level? If I talk it about this volume, that would be all right? Good? All right. While we're waiting for network and things, if you have already grabbed my repository, you should be able to go into Think Complexity 2, and then into the code directory. And if you are there, I am in the habit of launching a browser first, and then launching Jupyter, because then Jupyter grabs the last browser that you opened. And you should have this, which is the list of notebooks in Think Complexity 2. So that's part 1. And then part 2 is if you have access to the slides. And I recommend that you have either 2 windows open, one of them with Jupyter and the other one with my slides, or make friends with a neighbor and do a little bit of pair programming and have one of you with the slides and one of you with the notebooks. I'll leave it up to you to decide how social you want to be. But let me leave this up for just a couple of seconds, and I'll introduce Stuart Williams, who is helping us out. And we will take a couple of minutes to come around and help people get set up, and then we'll start the workshop part in 5 or 10 minutes once we have at least 70% of you with a working environment. So let me, if you show hands, if you've already got it going and you've got my repository and you've got Jupyter running, good. Still working on it. Still working on it and would like help. Or are you just waiting for things to download? Okay, we'll come around and help people who would like help, and we'll start in about 5 minutes. Okay, let's get started. Welcome to the tutorial on complexity science. I'm Alan Downey. If you have not yet connected to any of those downloads, you can get the instructions for setting up the software at the first link, and the second link is for these slides so you can follow along. Quick introduction of me. I teach at Olin College, which is just outside of Boston. It's a new engineering school that just started up about 14 years ago. Our mission is to fix engineering education. And one of the ways that I'm working on that mission is by taking some of the things that are not currently in the undergraduate engineering curriculum and trying to pull them in. And that includes Bayesian statistics, one of my favorite topics, and it includes complexity science, one of my other favorite topics. So I'm going to give you a quick introduction to complexity science. I'm going to introduce the first example, and then we'll jump into the code in a couple of minutes. So if you're still getting your environment set up, try not to pay attention to it for the first couple of minutes, and then when we're ready for the first notebook, we'll come around and again help you get set up. In the meantime, maybe the network congestion will clear up, we'll get some things downloaded and going. Complexity science, if you are not familiar with it, is modeling and simulation of complex systems, which is not a very helpful definition unless I also tell you what I mean by a complex system. This is the definition from Wikipedia. I'll give you a second to read that. So the two key elements of this are that you have systems with typically large numbers of things that are interacting with each other, and where the modeling of the system crucially has to describe the things and also how they interact. I'm going to put that on a little bit of a historical timeline. If you think about what physics has done, classical physics tends to focus on the left-hand side, which is the physics of simple systems that often involve very few things, like one hydrogen atom. But that by the time you get up to 3 hydrogen atoms, usually there's not a lot that we can do with classical physical models. On the other end of that spectrum are things like statistical mechanics, where you have very large numbers of things. And there, you may not be able to say much about what any individual particle will do, but you can describe groups using aggregation and make good physical models of what they'll do on average, or as an ensemble. Complexity science is the middle piece of this. It's not the very few or the very many, it's the interesting stuff that happens in between when you have lots. There's a lot of good stuff that happens in that space, but it has been historically not paid a lot of attention until recently. So the original classical physics, things like Newtonian mechanics, are pretty old at this point, from the 1600s. Even things like statistical mechanics and thermodynamics are from the 1800s. Complexity science is relatively new. It's really the late 1900s where we're going to start. We're going to start in about 1970. If you went through a pretty standard high school and college curriculum, you probably got up to about 1800. In high school, you learned Newtonian physics, and that got you up to about 1700. In college, you might have done thermodynamics and got up to the 1800s. If you did quantum, that got you into the early 20th century. But I'm curious to know, did anybody learn anything in college that was discovered after 1950? All right, good. But often not things like complex systems. And maybe I should ask that question too. Did anybody study complex systems in school? Okay, so my thesis holds up. I have maybe a tentative hand there. My thesis holds up that by and large in the undergraduate curriculum, there's not a lot of complexity science, which I think is too bad. This is useful stuff. It is interesting not just for the point of view of doing science, but also thinking about what science is. It's elegant stuff. Many of the models that we're going to look at today are very simple models that nevertheless tell us something about the world. They do useful work, and they're just kind of fun. So I've tried to choose the examples that have the biggest payoff for the amount of effort. I'm going to do 3 things today. We're going to look at agent-based models for about the first third. We'll take a break. We'll come back and look at cellular automata, take a break, and then random graphs. In between, there are a bunch of philosophical pieces of this that we'll take up and maybe have a chance to discuss a little bit. Ideally, at the end of this, at about 4:20, you'll have a good idea about what complexity science is, what it's useful for, and some of these philosophical questions that come up. I have a reading list for you at the end, so if I succeed and get you interested in this stuff, I have a list of books that you might want to pick up after the workshop. So the first section I mentioned is agent-based models. This is an article from The Economist a couple of years ago talking about the use of agent-based models in economics and a number of other areas. If you get a chance to read that article later on, I recommend it. The particular agent-based model we're going to work with is Schelling's model of racial segregation. And this is the one I mentioned is from the 1970s, so it's one of the first examples of work like this. Here's what the model looks like. You have a world that consists of a 2-dimensional grid with 2 kinds of people. So every cell in this 2-dimensional grid is either a red person or a blue person. And these people move around. By and large, they are happy where they are if they are surrounded by a few neighbors that are the same color that they are. But if they fall below some threshold, if they find that they are completely surrounded by the other kind of person, they become unhappy in the terms of the model, and then they choose a random empty location to move to. And that's it. That's the whole model. So this is where we'll get to the first thing that you get to play with code. If you start up Jupyter and point it to my repository, and then load chapter 9.ipynb, we'll start with the first section. I'm going to have you read through just the first section of that notebook called Schelling's model and run it. There are some animations in there. And if you have FFmpeg or another movie player installed, those animations should work for you. You might be able to get that working now. And I've got some instructions that are on the tutorial page that I linked to. If you can't get that working now, don't worry about it. If the animations don't work, I'll show them up here so you'll see them. And to be honest, if you don't run them, it's no big deal. So don't spend too much time trying to fix that. What I'm going to do, I'm going to go back and put up the links here. That first link is going to get you to this page that has some of the instructions, including the instructions for FFmpeg, which are here. A couple of different options there depending on what system you're running. And then if you're firing up Jupyter, I'm just going to show that process one more time. So if you've downloaded my repository, you should have a directory that's called Think Complexity 2. And a subdirectory called code. If you're in that directory, I recommend start up a browser and then start up Jupyter Notebook. If things go well, Jupyter should grab your browser and open this window for you. If for some reason it doesn't, if you go back to this window where you opened Jupyter, one of the things that Jupyter does when it launches is it prints this URL. And that's the URL that you can use to connect your browser to the Jupyter server that's now running on your laptop. So if you grab that URL and then paste it into a browser, it should do the same thing and open up a window that looks like this. So this is the Jupyter home, and it's currently showing the directory that contains the code for Think Complexity 2. If you scroll down and open up chapter 9.ipynb, you should be able to run through the examples in the book. I'm going to turn off the header and the toolbar, because that'll just give me a little bit more vertical space on the screen. You can do that if you need some space. I'm running in Python 2, but all of the code in this repo should work unmodified in both 2 and 3. If that turns out not to be true, let me know. If you have not used Jupyter Notebooks before, the magic thing to know is shift return. Shift return says, I want to execute the code that's in the current cell. So if I execute the first cell, it just executed my title, which doesn't really do anything. The second cell is going to try to import all the things that I need for this notebook. If you don't get any error messages, that means you've got everything you need, we hope. If you do, let us know and we'll come around and help you install things. If that's all working, then as I said, you should read through the first section here. Take a look at the code. I'm going to explain some of the code in a minute, so if there are things you see there that are baffling, make a note. We'll come to it in a second. Again, if things are working, you should be able to see animations. If not, let us know and we'll come around. We might be able to fix it. Maybe we won't. We'll see. And then the last section is this figure, which we'll talk about in a couple of minutes. Okay, let's get going again. Again, if you are still waiting for things to download or if the animations aren't working for you, try to tear your attention away for just a second. I want to talk a little bit about the model and what kind of work it does, and then we're going to come back to this notebook in a couple of minutes and do a couple of exercises. So let's go back to the slides. That's not what I want. That's what I want. Good. Okay. A couple of things here. I want to talk about the implementation of the model, how we coded it up in Python, and then talk about what kind of work the model does for us. Before I talk about the implementation, I'm going to use a bunch of NumPy stuff. How many people here have used NumPy before? Have not used NumPy? Okay, good. I think most of this will make sense. The first part of this is just creating the world, setting up a grid that has red people and blue people placed in random locations. It also has about 10% of the world that is empty houses that people can move into. So np.random.choice is going to create a NumPy array, which is just this two-dimensional grid. The choices are 0, 1, and 2, which represent empty, red, and blue. And the probabilities are 10% empty, 45% red, 45% blue. So that's part one. Questions so far? Good? Okay. The next part of this, I'm going to use a lot of logical arrays. So if you haven't seen this, when you do a comparison like array double equals 1, that's asking each cell in the array, are you equal to 1? The result is true or false, and so the output is an array of Boolean true and false values. So red is an array of Booleans that's true wherever there's a red agent, blue is true wherever there's a blue agent, and occupied is just any of the cells that are not empty, so I'm going to use that for choosing empty locations. Here's the interesting part. So each cell needs to look around at its 8 neighbors and count up how many cells there are that are like itself. And I'm going to do that using correlate 2D, which is a way of applying this kernel, that 3x3 array that says 1, 1, 1, 1, 1, 0, 1, is the kernel that I'm going to use as a counter. It's a little bit like a rubber stamp that I'm going to apply to each location in the array. And I've got a graphic here that shows how that works. So the kernel on the left is that little 3x3 small array. The input is the array that contains all of the reds and blues and trues and falses. And applying correlate 2D is going to take this kernel. For each location in the input, it's going to multiply the kernel times the input and then add it up. Okay? So if you have this particular configuration with all the 1s and the 0 in the middle, when you multiply by the array, everywhere that there's a 1, you're going to count that neighbor, and everywhere that there's a 0, you're going to not count yourself. That middle part is not counting yourself. So if I apply this to the red logical array, it will, for each cell, count the number of red neighbors. And then number neighbors, if I apply that to the occupied grid, that will tell me the total number of occupied cells out of 8. So both of these are out of a total of a possible 8. Is that clear? Questions about that? I think this graphic is the best I can do of explaining how correlate 2D works. If when we get back into the notebook in a second, you might want to read the documentation of that. That function is in NumPy, I think. When we get back to the notebook, I'll tell you where it is. Okay. The next part of this is figuring out which cells are not happy according to the criterion that I told you about before, which is that there's a threshold that I'm calling P. And if you have at least P% of your neighbors that are the same color as you, then you're happy enough to stay where you are. If it falls below P, you pick a random location and move. So fraction of red is just the proportion of neighbors that are red. Fraction of blue is the proportion of neighbors that are blue. Fraction of the same now uses np.where, which is one of my favorite and I think underused NumPy functions. Out of curiosity, who here has used np.where? Ah, okay. So this is very nice. This is an element-wise if statement that's going to ask, it's going to say where the first argument, red, is true. I'm going to select the corresponding element from frac red. And where red is false, I'm going to pick the corresponding element from frac blue. Okay? So it's a little bit like an if-then-else applied to each element of the grid. One of the nice things about using this in NumPy is rather than write a nested for loop with an if statement inside it, which would be relatively slow in Python, this is going to be pretty fast because that innermost loop is going to pretty much run at C speed. Okay, now let's take a look at what some of the results are. I'll show you the animation in the notebook, but this is kind of before, during, and after. The left one is the initial state where I've just put people at random. The middle one is after a couple of time steps, and then the third one is after enough time steps have gone by that I'm in pretty much steady state. People aren't moving around very much anymore. And the obvious feature of this is that I started with a world where people were scattered around at random. I've ended in a world where people are pretty segregated. If you look at any individual cell in that grid, most of the red cells are completely surrounded by red. Most of the blue completely surrounded by blue, and there tend to be empty houses that separate the neighborhoods. Again, if we run the animation, you can see that process happening. So this is running in a loop, and you see that it converges pretty quickly, and once it converges, it kind of doesn't change anymore. What this graph is showing is the degree of segregation as a function of how many time steps we've run. So everything starts at about 57%, which is that's what you get from randomness with a few empty cells. It's pretty close to 50. If there were no empty cells, it would be just about 50-50. With the empty cells, it's a little bit more, but that's where that's coming from. And then you can see what the effect of the different thresholds is. So P equals 0.2 means these agents would be perfectly happy if 20% of their neighbors were like themselves. So out of 8, that would mean that 2 out of 8, that would be 25%, perfectly happy with 2. But even with the threshold being pretty low, you still get a little bit of clustering, a little bit of segregation. But then something interesting happens at P equals 0.3. Again, that means I would be perfectly happy if 30% of my neighbors were like me. So out of 8, that would be 3 out of 8. That's 37.5%. I would be perfectly happy with 37%. But I don't get 37%. In this world, if all of the neighbors have P equals 0.3, I end up with 80% of my neighbors looking like me. So even though I would be happy with 3, I end up with about 7 out of 8 of my neighbors looking like me, which is a pretty high level of segregation. Again, that's what that graph looks like. Before I go on, any questions about that graph and how to read it and what that means? It's good? Okay. This, again, is this striking result. Okay, I claim that it's a striking result. You may well be sitting there thinking, so what? And in particular, you might be thinking that this is a ridiculous model. The world is complex. People are complex. This is not how people decide where they're going to live. It's not a two-dimensional grid. Different people are different from each other. Houses are different from each other. It does not seem like this model could possibly tell us anything useful about the world. I'm going to claim that it does, but we'll get there. Before we get there, I want to back up and talk about explanatory models. Explanatory models answer why questions. If you want to know why cities are so segregated, Schelling's model might tell us about that. If you want to know why planetary orbits are ellipses, you want an explanatory model that answers that question. So I'm going to talk about classical mathematical modeling as a way of contrasting it with complexity science. Classical stuff is based on physical laws, usually continuous mathematics like differential equations, and usually derivations that kind of look like mathematical proofs. So the example that I mentioned, planetary orbits look like mathematical ellipses. And you might naturally ask why, and Kepler did. and answered it. He said, look, if you've got these natural laws, if you know the law of universal gravitation, and you have Newton's laws of motion, then you can write a differential equation that describes the motion of a planet as a function of time. You can solve that differential equation, and that derivation shows you that the answer looks like an ellipse. And that feels like a very satisfying kind of explanation of the world. It sounds like that's why orbits are ellipses. Put a stamp on it. We're done with that question. In part because when you write a mathematical derivation like that, it feels like a proof. It feels a lot like we have proved something about the world. But I want to nudge at that a little bit. I want to try to talk you out of that position, and in particular, remind you that you didn't actually prove anything about the world. You proved something about a mathematical model. You proved that if the planet behaves like a point mass, if the sun is much bigger than the planet, and if there are no satellites like moons, and if there are no other planets that are nearby and big enough to influence you, then the result looks like an ellipse. But in fact, none of those assumptions are actually true, and in fact, planetary orbits are not ellipses. If all of those things are approximately true, then the ellipse model is a pretty good one, but it's not strictly true, and that's part of the reason I claim that you haven't really proved anything about the world. But then you might wonder, why should we think that anything about this model is true in the world? The world is not obligated to behave according to our models. Here's my claim, which is that fundamentally we're making an argument by analogy. We're saying that the world is similar to the model, and therefore what happens in the world is similar to what happens in the model. I use this diagram sometimes. The thing that you're describing is in the lower left, so that's the world. That's the system that you're interested in. It's your job to choose a model. And the process of making a model is called abstraction, because you are abstracting away or subtracting away details in order to make a model that is simpler than the world. The reason that that's useful is that with a model, you can do things like mathematical derivations. You can predict that there's some kind of behavior, and then you can do a comparison between the behavior in the model and the behavior of the actual world. So this framework, I claim, is how explanatory models work in the context of classical models. Again, it's an argument by analogy. It's all based on the assumption that you're making good decisions about what you need to include. You have to include all the important factors, and the things that you leave out need to be less important. But those are qualitative decisions that you have to make as a modeler in order for your model to do what you want it to do. All right, coming back to Schelling. Schelling's model is not like the real world. It is not realistic. So it begs the question, what kind of use is it when it's so wildly unrealistic? I've been asked this question. I actually had a version of this question on a first date in May 1989. I mentioned I was from Boston, and I got a question that was something like this. I don't remember the exact wording, but it was something like, you're from Boston. Boston is a highly segregated city. Bostonians must be kind of racist. Which kind of put me on the defensive. I wasn't sure how to respond to that. But let me ask you, thinking about Schelling's model, does Schelling's model give you anything that you can say to this hypothetical date in 1989? Or more broadly, does Schelling's model tell us anything about the world at all? Or is it just such a ridiculously simple model that it's a mathematical toy, but who cares? People don't have to be that racist to result in segregation. Interesting, yeah. Thoughts? So what does that mean? What can I say to my date on the basis of that? All right, so the date is unrecoverable. But if Thomas Schelling was there, I think actually he might say something similar to what you just said, which is just because you see segregation in a city, you may not be able to say much about the people in the city. It may be that the effect you're seeing is not just because of how the agents individually are behaving, but because of how all of those behaviors add up to a systemic effect. And I don't know how to describe somebody. If someone says, I'm perfectly happy if 3/8 of my neighbors are like me, but I start to become unhappy if they're not, maybe that's xenophobia, maybe it's a mild bit of racism, maybe there's an affirmative version of that that just says, I like to have people that participate in the same activities I do, and maybe that doesn't make me a bad person, I don't know. But that seems very different from someone who says, I want 80% of my neighbors to be like me. So I don't know if I'm defending Bostonians or not. I don't know if I can necessarily point to any given city and say that this city is segregated because the residents are racist, and that city is segregated because of Schelling's model. So it doesn't necessarily give us that kind of specificity. Yep. Ah, interesting. So, there could be, and you could do that model. In fact, we're going to do some exercises in a minute, and that's something that you could try out yourself. The suggestion is, how about a model where instead of everybody has p equals 0.2, maybe 20% of the people have a threshold, maybe a low threshold or high. There could be variability between agents. Yes, and one of the things I'm getting to is that a nice thing about these models is if you want to try out those kinds of what-if scenarios, you can often do it with just a few lines of code, as opposed to many classical models where sometimes the simple thing, yeah, you can do the analysis, you can do the derivation, but as soon as you tweak it, now all bets are off. So we'll do some examples in a minute, some exercises in a minute. In fact, now. So let's go back to the notebook, chapter 9. Take the code that I've given you now that we've looked at the implementation. There are a bunch of changes that you could try out. A simple one is just to change some of these proportions. So we started with 45%, 45, and 10. You could try it with a world where there's a majority and a minority and see how that affects what the model does. That one's a very simple change. And then I have a couple of optional exercises if you want to try them that will take some more substantial changes. One of them is maybe what if there are 3 kinds of people? See what that does in your model. And then the other one I want to suggest is a world where people actually like diversity. So try it, give everybody 2 thresholds where I'm unhappy if I'm unhappy if nobody's like me, and I'm unhappy if everybody's like me. I'm only happy in the middle, and see what happens. So try out some of these exercises, play around with the model a little bit. I'll come around. If you're still getting things set up, we can work on that, and we'll start up again in 5 or 10 minutes. I'm going to let you get back to this in a second. If you like, you can keep working on that exercise, or if you go back to the notes, there's one other thing you might want to check out. Has anybody read Bill Bishop's book called The Big Sort? If you're not familiar with this, his thesis is that the US is increasingly becoming segregated by political affiliation. People are more and more living with and surrounded by people who are either also Democrats or also Republicans. And his suggestion is that at least part of the mechanism is that when people move, they might look at a couple of different locations and pick the one that has some people who are similar to them. So this is kind of the flip side of the Schelling model, where instead of people becoming unhappy and deciding to move, this is just saying, if you've decided to move because of random life events, the location that you choose might depend on what the neighbors look like. So if you're interested, this is one of the exercises that's in Think Complexity. There's a solution to it that's in chapter 9 solution.ipynb. So if you want to keep playing around with chapter 9, feel free to do that, work on the exercises. If you're curious about the big sort, you could open up chapter 9 solution.ipynb. I've got an implementation of Bill Bishop's model, or maybe I should say a model that's based on a very abstract version of Bill Bishop's thesis. And then you can see what effect it has. In particular, there's a parameter, which is the number of houses that you look at. So maybe you just look at 2 different houses and you pick whichever one has the most people like you. Or maybe you look at 3 houses or 4. And in the same way that we looked at what happens when you vary the threshold, we'll look at what happens when you vary the number of houses. So take a look at that. It's in chapter 9 solution.ipynb. And again, we'll regroup in a couple of minutes. Okay, let me interrupt you again. I want to wrap up the big sort and wrap up agent-based models, and then we'll take our first break. Just a couple of things to look at. If you run big sort, what you see is an effect that's pretty similar to the shelling model. It doesn't matter too much whether people become unhappy and then move at random, or choose to move at random and then they're selective about where they go. You get pretty much the same effect either way. And with a surprisingly small number of houses that you look at, even with n equals 2, meaning that when you move, you look at only 2 houses and you choose whichever one has more people like you still get a lot of segregation. And this graph shows you the result. With k equals 2, you end up at about 70% segregation. With k equals 3, you're now into the mid to high 80s, which means that almost everybody is completely surrounded by people like themselves. And typically people do look at more than 3 houses. Maybe they don't choose exactly based on the neighbors, but if this is one of the factors that influences their decision, it seems like even a kind of a mild factor can again yield a systemic effect that's much stronger than what the individuals are actually doing. So this is my first example of agent-based models. One of the things that I mentioned that you see from these experiments is if you want to ask what-if questions, if you want to tweak the model, try out different behaviors, it's relatively easy to do that compared to classical modeling, compared to trying to do analysis. If you imagine writing differential equations or trying to prove the behavior of these systems, that would be much harder. Writing computer simulations tends to be kind of quick, relatively easy for people who know Python at least, and you can try out a lot of scenarios. So that checks off the first item in the outline. We're going to come back in a couple of minutes and talk about cellular automata. We'll take a break for 10 minutes. I've got 2:20, so let's start up again at 2:30, and we will look at the game of life. Okay, let's get back to it. What I have running up here is one of the examples that we're going to look at now, which is called Game of Life. I'm going to shut this down. We'll come back to it in a couple of minutes. If you go back to the slides, here's part 2, which is Game of Life. This is also from 1970, so we haven't quite made it into the 21st century. John Conway is a mathematician who came up with this model, and then it was popularized in a Martin Gardner column in Scientific American. Anybody here old enough to have read Martin Gardner in Scientific American? Okay, good. Good stuff, if you want to go back to it. The model is similar to Schelling's model in the sense that it's a two-dimensional grid, and each cell has a couple of different states. So in the Schelling model, it's red, blue, or empty. In the Conway model, in Game of Life, every cell is either alive or dead. So metaphorically, you can think of that as that either there's an agent in the cell or there's not an agent in the cell. But in this case, the agents aren't going to move around at all. So maybe don't think of them as agents, just think of them as a cell has two states, alive or dead. And here's what's going to happen in each time step. I'm going to look at each cell and count the number of neighbors. And if the cell is currently alive, and I have either 2 or 3 neighbors, then I stay alive. If anything else, if I don't have enough neighbors, I die. If I have too many neighbors, I die. Okay? The other possibility is if I am currently dead, or if the cell is currently dead, then I need exactly 3 neighbors. If I have 3 neighbors, I come to life, and anything else, nothing happens. I stay dead. Those are the rules. And in fact, those are all the rules. So you can think of this as like a world that has very simple physics. So there's no universal gravitation in this world. Nothing moves. The only thing that happens is just the state of the cells flips, depending only on the immediate neighborhood, only on the 8 cells that are nearby. So take a look in chapter 6.ipynb and run the first section, which is called Game of Life Entities. And then there's a section there that's called the R pentomino that starts out with one initial configuration, which is 5 cells that are on and everything else off. When you get there, you can try out some other scenarios. So try adding a few cells, removing them, change the shape, and see what happens for different initial conditions. And I'll show that up here, and you can follow along there. So it's chapter 6.ipynb. And then this is the section I mentioned a minute ago. This is the R pentomino. So if you change some of these 1s and 0s, you can get a different initial configuration, and then you can run that and see what the output looks like. Give you a couple minutes to work on that, and as usual, I'll come around if you have any questions. All right, let me get you back. If you had a chance to play with this, you might have seen this animation. This is 1,200 time steps, starting with 5 cells. If you start with 5 cells that are configured in the R pentomino shape, it runs for 1,200 steps, and you get this. But if you fiddled around with it a little bit, if you change one cell, so I just pulled out the middle one, change the middle cell and run it again, this takes a little while to compute, we're going to get a really boring animation. Basically, everything just dies after about 1 time step, and then once everything's dead, nothing can come back to life. That's it. There's your animation. So this game of life world is wildly nonlinear in the sense that a very small change in the initial conditions yields wildly different results in what happens over time. But there are a bunch of these entities that people have either discovered or invented. A lot of these happen naturally. If you start from a random starting state, very quickly you're going to see things like the block, the beehive, the loaf. People have given names to a lot of these things. This set, these are all stable configurations, which means if you have 4 cells all by themselves and nothing nearby, in the next time step, you're going to have those same 4 cells because each of them has 3 neighbors, and that allows them to stay alive. Same thing with the beehive. Each of them has either 2 or 3 neighbors, so that's enough to stay alive. So those things are called still lifes because they don't move. And then there are things like oscillators. So the upper left there is a blinker, and that just says if you have 3 cells in a row, the 2 cells on the outside will die, but the 2 cells on the top will come to life, and back and forth. And so it looks, at least to our eye, like it's spinning. It's not really spinning, it's just cells that are going on and off, but it looks like it's spinning. And in that case, the period is 2, which means that after 2 time steps, you're back where you started. There are other things like the pentadecathlon that have a period of 15, so it takes 15 steps. There is a 53 period oscillator out there, so you can look that up. There are a bunch of these that people have discovered. And then there are these interesting things called spaceships that are periodic in the sense that the glider, for example, looks the same after every 4 time steps. So it has a period of 4, but after 4 time steps, it has translated down and to the right by 1 cell in each direction. So if you watch it over time, it seems to move through space. And again, it's not really moving through space because, again, cells don't really move. They just turn on and off. So what we look at when we see a spaceship moving is a kind of cognitive illusion, which makes us wonder whether these spaceships are really things at all. We've given names to these entities, but is it just like constellations where we see a random configuration of stars and we give it a name and there's not really anything there? Or do these things have some kind of existence? Does it make sense to talk about spaceships? Turns out this is a really old philosophical question. It comes up over and over by different names. You might have heard of either George Washington's axe, where the handle has been replaced 3 times and the head has been replaced twice. And so you naturally wonder, in what sense is it George Washington's axe? Because all the parts have been replaced. It goes all the way back to the ship of Theseus, which is among Greek philosophers one of the examples that they used. Again, every plank, every connector on the ship had been replaced. In what sense is it still Theseus's ship? I mentioned this is an old question. This is a 2,500-year-old question. Heraclitus wrote about this in Greek, so that is patomois, tois, autois, something like that, which is translated there as, we both step and do not step in the same rivers, we are and are not. You might have heard there's a version of this. People often say you never step in the same river twice, but I think that dilutes what Heraclitus is getting at here, which is that this is not about rivers. This is about everything. Everything is constantly in a state of change or flux. You are not the same people you were 10 years ago. Probably every cell in your body has been replaced, so in what sense are you still you? You're not made of the same stuff. This is an example I love to talk about, but at some point you have to stop because complexity science is a philosophy black hole. All of the stuff eventually gets you face to face with various questions in the philosophy of science, none of which have been resolved, none of which we are likely to resolve in the next hour and 20 minutes. Although I like to bring them to your attention just because I think they're fun to think about. Complexity science is very much like Wikipedia. Are you familiar with the getting to philosophy conjecture? This is the conjecture that if you start on any Wikipedia page and click on the first link and repeat that process, you will eventually get to the page on philosophy. And there are usually a couple of rules, like you're not allowed to click on the italicized links or the things that are in the little Wikipedia sort of meta boxes. It has to be part of the article. If you will play along with me, I'd like you to try this out by starting from any random Wikipedia page you can think of and apply these rules, and let's see if it turns out to be true. Let me fire up a browser. Someone want to give me a topic? Wikipedia, Jackie Rob. Of course, all of this will be predicated on a working network. Come on, network. All right. Starting from Jackie Robinson. This might take more time than it's worth. We'll see. Most things will get you there in about 6 hops or fewer. All right, so the first real link, the italicized one doesn't count. The first real link is baseball. Bat and ball game. Well, game would get us there pretty quickly if we get to game. Bat and ball game, similar to golf. Yeah, okay, we're wasting a little time here on games, but we'll get there. Golf is, sport is going to get us there very quickly. Sport gets us to nothing in parentheses, that doesn't count. Competitive. This is a longer path than most I've tried. Territory. Ethology. Now we're getting there. And that move is part of the reason that this is true, which is that many definitions begin by giving you something that is more abstract, of which the thing is an instance. So you have a tendency to go up and up in abstraction, from ethology to scientific, to techniques, and I think we're going to get there soon. Systematic. Come on, don't make a fool out of me. Critical thinking. Definitions. All right, I give up, but you can play this game yourself sometime. Anyway, so that is complexity, as I said, is a bit of a philosophical black hole. Getting back to game of life, one of the things that's interesting about the game from a mathematical point of view is this question about what happens when you get to steady state. Most initial configurations are like the R pentomino. Actually, I should say, most configurations don't do anything very interesting at all. They very quickly either just die out completely or come to a steady state where everything is either a still life or a blinker or maybe a couple of spaceships that are just going off toward infinity. A few things run for a really long time, like the R pentomino, and in a couple of minutes we're going to run rabbits, which is another one of these simple initial configurations that does a lot. But everything seems to get to steady state eventually, and so Conway asked an interesting question, which is it possible to have an initial configuration that will yield an unbounded number of cells, a number of on cells? In other words, it never comes out to a steady state. Yeah? 11 steps from where? From list of animal names to philosophy in 11 steps. Very good, thank you. Very good, all right. All right, so that was Conway's conjecture, and just to get people going, he posed as a conjecture that there are no initial conditions that will get you to an infinite number of cells. So just to give an example of what I'm talking about, if you run life rabbits, there's a file in the repository. If you go to the command line, you should be able to just run it by saying python liferabbits.py. From within Jupyter, you should be able to execute it by doing this %sx and then Python liferabbits.py. Give that a try. I will run it here and see what it looks like. So this is an initial state of about 9 cells. And it runs for a good long time. I forget exactly how long. I think it's about 10,000 time steps. If you click on that link about Methuselahs, patterns like this are called Methuselah because they're very long-lived. And they often produce a large number of on cells. This will go for a while. You can see that it spontaneously produces some of the patterns that we saw, a lot of the blocks and loaves and boats, things like that. There's a spaceship flying off toward the upper right, another one going off toward the upper left. They always move on the diagonal. They can move on any of the 4 diagonals. So that's going to run for a while. So that's what got Conway to his conjecture, which is some of these things seem to run for a very long time. Do any of them, in some sense, run forever? And what we mean by forever is constantly producing an increasing number of cells. You can think about what kinds of patterns, how would you do that? If you were trying to design a pattern that would produce an infinite number of cells, how would you do it? Thoughts? Yep. Something that behaves fractally. So the first comment was something that behaves like a generator. So if you are constantly producing spaceships, and we saw that rabbits produces spaceships. It looks like there are about 6 or 7 of them, 5 maybe, that rabbits has already generated. So if you could have a pattern that just constantly generates things, if you could have a pattern that's fractal, that's interesting, meaning that it would sort of grow and occupy space in a lacy kind of pattern where the things stay alive. Yes. Yep. Yes. So you want something stable in the middle and a boundary that expands. That might do it. Yes. And in general, those are the 2 ways to do it, which is if you, in some sense, your pattern stands still and produces lots of gliders, that would do it. Or if you have a pattern that can move through space either as an expanding boundary or just a linear feature that moves through space and leaves detritus behind it, then that would do it as well. And I'm curious, I suspect since many of you have seen Game of Life, you probably know that Conway's conjecture was in fact refuted and he had to pay his $50. Now, I should say, I think Conway probably would have guessed that these patterns would exist. He just wanted to prompt people to find them. Bill Gosper is, I think, the first person. He worked with a team of people to produce this pattern, which is called Gosper's gun. And the thing in the top left, so the top row there, is a periodic oscillator, but after each period, it has produced a glider. And so there's an infinite stream of gliders that will come shooting out of that. Now, one of the things about this, designing things like this is very difficult because of the pattern that you were just talking about in the back row, which is that you could have a still life and an oscillator, and if they are isolated from each other, then they behave in very predictable ways, but the minute they collide, all heck breaks loose and they are very unpredictable. So in this case, you can see that there are some pieces there that look familiar. There are these 2 blocks on either side, those are kind of stable, and 2 spaceships in the middle that are propagating back and forth. And what they designed was a spaceship that when it collides with a block reverses direction, and then 2 spaceships that when they collide, they reverse direction and produce a glider. So in some sense, they're able to assemble this from pieces, but when you take 2 well-understood pieces and put them together, they do not behave in well-understood ways. That, from an engineering point of view, is a nightmare, because one of the fundamental tools of engineering is isolation. the ability to design subsystems and then put them together and have them interact with each other in simple, predictable ways. That is like the opposite of game of life. So one of the things we'll come back to in a minute is not just the philosophy of science, but in some sense the philosophy of engineering. How do you do design in an environment like this where isolation, the fundamental tool of all engineering, has been taken away from you? Okay. I think that's all I want to say about game of life for now. I want to drop down a level and talk a little bit about how I implemented it in Python, because there's a little bit of NumPy cleverness that I want to show off here. If you go back to the notebook and you read the section that's called Implementing the Game of Life, let me walk you through the code first, and then I'll give you a couple minutes to look it over. Initializing the array is very similar to what we saw before. I'm just using a random initial start with just 2 states. That's what the 2 is, and it's 10 by 10 grid. This is what it would look like if you wrote this in terms of basic Python, not using NumPy. So I've got nested for loops. So I'm going to go through each row I and each column j. I'm going to use a slice operator. So the line that says neighbors equals a bracket, that's the slice that pulls out a 3 by 3 chunk, adds up the neighbors, and then the if statement is, those are the game of life rules. So if I'm alive, I need a 2 or a 3, and if I'm dead, I need exactly 3. So that's it. It works. It's correct. It's really slow. And now we're going to see if we can speed that up using NumPy. Trick number 1 is our old friend correlate 2D. If you want to add up your neighbors, here's a simple way to do it. And now I can use some logic that says, if I'm alive and I have exactly 2, then I'm good. And if I'm, I think I said that wrong, but you can probably read the code better than I can say it. Okay, so this is the same thing using logic. It's a little bit slow because every time you do one of those logical operations, you have to create a new array. So this, when you say c equals 3, that creates an array. C equals 2, that creates an array. And then you AND it with a, that creates an array. And then you OR that result, that creates an array. So there are 4 temporary arrays there that get created. We want to see if we can do a little bit better than that. Here's an intermediate step that actually makes it worse, but then we'll make it better again. It makes it worse in a slightly funny way, which is instead of treating alive and dead cells as special cases, I'm going to make the whole thing one case instead of 2 cases by putting a 10 in the middle. So my old kernel had 1 for all the neighbors and 0 in the middle. So the old kernel just counts the neighbors. The new kernel has 1s for all the neighbors and 10 in the middle. Why on earth am I doing that? It's going to be 10 for me and between 0 and 8 neighbors. So if that total sum comes out between 0 and 8, that means that I'm dead and I have 0 to 8 neighbors. If I'm alive, I get 10 points plus my neighbors. So if the result is anywhere between 10 and 18, that means I'm alive and I have 0 to 8 neighbors. So I've encoded both my state and the neighbor's state in a single number between 0 and 18. And I could have cheated a little bit. I'm currently not using 9. 9 is not possible. So I could have packed this a little bit more densely, but because we have 10 fingers and we think in decimal numbers, this makes things simpler for us to think about. This is now useful because instead of using these logical operations, I can now use a table lookup. So I'm going to create a table that has 20 entries in it. They're mostly zeros, but I'm going to put a 1 at locations 3, 12, and 13. Because those are the states where a cell comes alive. State 3 means I'm dead and I have 3 neighbors. State 12 means I'm alive and I have 2. And state 13 means I'm alive and I have 3. And those are the states where I should create a new cell. So this now is very fast. I just need to do the correlate 2D and a table lookup. I minimize the number of intermediate arrays that I create. And if you run life.py, that was the example that I was running during the break. That is an array that is, I believe, 1400 by 1000 pixels. And on my not super powerful laptop, it runs sort of 10-ish frames per second, I think. I haven't actually clocked it, but it runs reasonably fast on a pretty large array. So if you ever find yourself in a fight with someone telling you how slow Python is, I want you to break out this example. So have this running on your laptop at all times and show this to them. Because if you coded this up in C, it would probably run about 5% faster. Because the Python overhead on this is practically nothing. All of the work is being done inside NumPy, which is written in C. Actually, some of NumPy deep down inside is Fortran. Not this part, though. Good. Any questions about that implementation? All right, so keep these NumPy tricks in mind anytime you're implementing things like this. Here's an exercise that you can do if you want to get back into the notebook, which is that table that I just showed you makes it very easy to encode any rules you want. Conway chose that particular set of rules because it just turned out to be interesting. But there are other variations that also have some interesting behaviors. One of them that you can try out is called high life. It's the same set of rules, but with one additional rule, which is if you are dead and you are surrounded by exactly 6 live cells, then you come to life. And you can implement that rule just by adding one more entry into the table. So try that out and see what some of the initial patterns do with that new set of rules. And as always, we'll come around, and if you have questions, let us know. This exercise might be easier to do just by editing life.py rather than working in the notebook. So if you want to open up life.py, you can find the code right here that we were just looking at. And as I said, the change is very simple. You can add as many numbers in here as you want. I added that 6, but you can try out some different rules. And then on the command line, if you want to run. So I've never tried this before, but this is the example that we started with. Or let's do rabbits, actually. So this is rabbits. It does really interesting things under life rules. Let's see what it does under high life rules. Meh. Now, one way to approach this is, okay, so here everything died, so maybe let's make it a little bit easier to live. Let's add more live cells. So let's maybe add 14. What happens if we add 14? Interesting. Oh, but I lost the guy in the back row who asked about the fractals. So if you don't have enough rules that create live cells, typically everything just dies. If you have too many things that create, then it typically just explodes. And the interesting thing about Conway's rules is that they're right on that boundary. That some initial conditions vanish, some initial conditions grow forever. And that's one of the themes that comes up over and over in complexity science, is this idea of being in an intermediate regime between boring on one end because everything dies, boring on the other end because everything lives, and interesting in the middle. I think maybe I'll stop this before it takes over the world. So play around with that a little bit. We'll get started again in 2 or 3 minutes. Okay, I want to wrap up this segment, and then we'll take our second break. If you want to play around with it some more during the break, you can do that too. There are a couple of recurring themes that come up. I mentioned one of them, which is that boundary between boring at both ends and interesting in the middle. The other one that comes up over and over is that you can have these worlds that have very simple physics. Just a couple of rules that describe the whole universe, and yet very interesting things happen. And the other is this idea of emergence, that you can have entities that appear at a high level that in some sense don't exist at a low level. Spaceships sure look to us like they are a thing. They're not a thing. There are no spaceships in Game of Life. Nothing in Game of Life moves. But yet we have the emergence of things that appear to move. That is a recurring theme in complexity science, is that kind of entity. And a lot of the things that we describe in the world, like a hurricane, for example, a hurricane is a pattern. It is a way that air and water are behaving. And if they behave in a certain way, we point at it and say, that's a hurricane. But it's not clear what the that is that we're pointing at. It's not, for example, a collection of air molecules. And in the same way, your body is not a collection of cells, and so on. There are many examples like that. About the first point, about simple rules, Stephen Wolfram has written a whole book about this, about the idea that these worlds with simple rules can yield complex behavior. I'm going to give you a second to read that quote. And if you're interested, this is one of the books I'm going to recommend at the end for more reading about this. Wolfram did some of the early work looking at very simple cellular automata, even simpler than Game of Life. Game of Life is two-dimensional. Wolfram started out with just 3 dimensions. Sorry, just 1 dimension, less than 2. 1 dimension, 3 neighboring cells. So each cell plus its 2 neighbors. And it turns out that with just 1 dimension and 3 neighbors, or actually 2 neighbors, a cell and its 2 neighbors, you can generate systems that produce truly random numbers, and you can generate systems that are Turing complete, that can compute any function that is computable. And both of those are fairly astonishing claims. Again, Wolfram's book gets at that. And then the other thing I mentioned is this idea of emergence, that you can have things at a high level that appear like entities. We describe them, we understand how they work, and yet at a low level, in some sense, they don't exist. One of my favorite examples of this, if you are in a helicopter and you look down at a traffic jam, the traffic jam propagates backwards over time. The chunk of cars that are stopped tends to move in the opposite of the direction of travel. None of the cars are going backwards. All of the cars are either standing still or going forward, but the emergent entity, the jam, propagates backwards. There are a bunch of other examples. This is a nice web page called Emergent Universe, and during the break, if you like, you can explore there. They have lots more examples of this. We will resume. I've got 3:10, so we'll come back at 3:20. Okay, we'll get started again in about 2 minutes if you're coming in and getting settled. Okay. If you got a chance to check out some of this Emergence stuff during the break, it's good stuff. Get back to it later if you get a chance. We are moving on to part 3. So we've done agent-based models, we've done cellular automata, and up next, random graphs. I'm going to motivate this by asking this question. Are you popular? The answer is no. Part of the reason I know this is that you're at this conference. But the other part of the reason that I know this is this article from Scientific American. This came out in 2011, so we have made it into the 21st century. This was why you are probably less popular than your friends, and there's this funny cruelty in social networks, which is that if I go into your social network and I randomly pick one of your friends, and then I ask, who has more friends, you or that random person I just chose, it will turn out that about 80% of the time, it'll be them, not you. Which seems very strange. It seems almost paradoxical, but it is true. To understand why this happens, we're going to do a bunch of graph algorithms, and in particular, we're going to use NetworkX. Have people played with NetworkX before? Okay, good. If you did Eric Ma's workshop this morning, you definitely played with NetworkX, but it sounds like several of you have. If you haven't, we're going to do a little bit of quick introduction. Fundamental idea of graphs in this context is that you have a set of nodes and a set of edges. If we're talking about social networks, each node represents a person, and each edge represents a friendship between two people. So this social network has four people in it, and 3 of them are friends with that popular person in the middle, and the other 3 of them have only one friend each. A big part of what we're going to talk about is the degree of a node, which in the context of graphs, the degree is the number of edges that are connected to a node, and in the context of social networks, the degree is the number of friends that you have. We're also going to talk about the degree distribution. So if I look at a whole group of people, if I look at a social network, I could count up how many friends each person has, and then count up how many people there are with each friend count. And that's what this degree distribution looks like. If you're familiar with probability mass functions, this is a probability mass function that shows me that for degree 1, there are 3 people. 75% of the people have degree 1, meaning they have one friend. And then there's one person, 25% of the population, has 3 friends. So this graph represents the degree distribution. If you think of it like a Python dictionary, it's a mapping from the degree to the fraction of people that have that degree. And if you go to the notebook called social.ipynb, it will walk you through a quick exercise to do what I just did, and then you're going to add a few more edges to that graph and see how it behaves. And I'll do it up here, and you can follow along. Social.ipynb. And you should run the first section, which is called graphs, and do the first exercise. On? Is my mic on now? It is, okay. And we're back. So if you don't mind, for the benefit of the audience at home, I'm just going to run through that again one more time quick. So again, I added an edge from 4 to 0. I added an edge from 4 to 1. So now my graph looks like this. I've got two nodes with one friend each. I have two nodes that have two friends each. And I have one node that has exactly 4 friends. And so if I run the rest of the cells, I can get the distribution of degrees, and it looks like this. Again, that's 2 people with 1 friend, 2 people with 2 friends, 1 person with 4 friends. Questions so far? Good. Okay. Obviously not very interesting when we have a graph that's that size. Let's get up to a somewhat bigger graph. This is data from Facebook. It's old data from Facebook. I forget exactly when this was collected, but it only has 4,000 people in it, so it's certainly not the size of Facebook now, which I think is at something like 2 billion. Whatever, it's not 4,000 anymore. But we can work with this data set. It's a decent size. If you will go back to the notebook and run through the section on Facebook data, and then do the first exercise that you get to, again, we'll come around and help, and we'll go over it in just a minute. Okay, let's take a look. So this graph has 4,000 people in it and about 88,000 edges. So on average, I think there are about 20 friends per person. This is the degree distribution if I go through and I select people at random so that everybody is equally likely to get sampled. This is what the degree distribution looks like. And it shows that a lot of people have a small number of friends. The majority here looks like it's less than 100. There are a few people who are in the 150 to 200 range, and then there's a very thin tail there of a small number of people who have 400, 600, 800 friends. Okay? And then there's some code here that does the random sampling that I talked about a minute ago, where I pick a person, and then I pick one of their friends, and then I count how many friends that person has. And if I compute the degree distribution for those people, it looks like this. Let me go back to the slide so we can do a little bit of side by side. This is totally random people. This is friends of totally random people. Random, friends of random. So two things happen there. One is I get a much thicker part of the distribution that is in the hundreds. Instead of a small number of people at 100, I have a large number of people at 100. And the tail gets a lot thicker. Here the tail is so thin I can barely see it. Now I have substantial numbers of people who are showing up in this sample who have hundreds of friends. So what's going on here? Why are these two sampling processes so different? The reason is we're not sampling representatively when we sample friends. So if I just pick people at random, everybody's equally likely to appear in the sample, and so I'm getting an unbiased view of what the population looks like. I'm getting the true representation of the degree distribution in the population. When I sample friends, I'm more likely to land on somebody who has a lot of friends, because every edge that leads to you is another possibility that you will be selected. And in fact, your probability of being selected is directly proportional to your degree. The number of friends you have is like votes that you get, is like more chances that you get to appear in the sample. And as a result, people with a lot of friends are more likely to show up, and that's what causes the shape of the distribution to look so different. And that's also what causes the original effect that the Scientific American article talked about, which is that your friends are more likely to be popular than you. In the Scientific American article, it was about 85%. In this particular data set, it's lower. It's around 66%, but the effect is the same. So this is an example, that pattern of over-representing people in proportion to their degree is an example of the inspection paradox. And this comes up all the time. There's an article here that I wrote a number of years ago that's just a list of all the places where this phenomenon happens. It happens in social networks. It happens in class size. If you look at a school, if you go to a college and you ask the dean, how big are your classes? The dean will say, oh, we have a lot of small classes, we have some medium-sized classes, we have a few large classes, and the average class size is 25. But then you go to the campus center and you pick random students as they go by, and you ask them, how big is your class? How big is your class? And you write down all the answers. That whole distribution is going to be shifted to the right, and the mean, instead of being 25, which the dean told you, might be 35 or 40. And you'd go back to the dean, and you say, you're lying. Your average class size is not 25, it's 40, and I know because I asked the students. Who's right? In some sense, you are both right, but you are averaging across different populations. The dean is telling you the average where each class gets one vote. The students are telling you an average where each student gets one vote, and therefore classes that have a lot of students in them get voted high, overrepresented in the sample. And if there's a seminar out there that only has 2 students in it, the chances are it doesn't show up in your sample at all. I'll let you should check out this article later if you're interested. I'll just give you one more example because it's kind of fun. When I teach statistics at Olin, I ask people, how many children are there in your family? And we always have to be a little careful to define children and define family, but for some definition, I ask everybody, how many children are there? I write it all down, I compute the average, and it usually comes out to something in the high 2s, like 2.7. The average number of children per household in the US is something like 2.3. So it's always higher in my sample than in the national average. And I ask the students, why is that? Why are Olin students apparently coming from bigger families? And they make up all kinds of stories. They tell me, well, they're relatively affluent families and the families are bigger, or the Northeast is overrepresented in family. There's always an explanation, except that it's purely an example of the inspection paradox. Again, families with a lot of children in them are more likely to be represented in my classroom just because they have more lottery tickets. Or you take it to the other extreme, a family that has no children at all will not be represented in the sample. And so immediately, because I've lopped off all the zeros, the average shifts up. So it's another example of the inspection paradox. Again, you can read more about it if you like. So this is the first part of the explanation. And this effect is stronger depending on how thick the tails are. So actually, if there's no variability at all, if every class size is exactly 25, then the dean's average and the student's average would be the same. But the more variability there is, the longer those tails are, the stronger this effect becomes. So in social networks, it's a very strong effect because of power law distributions and scale-free networks. And that's the next thing that we're going to talk about. So I have to explain power law distributions. And to do that, I want to start with a bunch of different distributions that I'm writing down as f of x. So what f of x means is the probability that degree is equal to a particular value of x. And that was the examples that we saw a minute ago where we were looking at these distributions. If you think of this, x is the number of friends, and the vertical axis is probability. So that function there is f of x. And in general, it kind of looks like a mess. Like, that's not a simple mathematical function. I could fit a curve to it. Maybe I could use splines or something like that. But there's not a simple mathematical description of what that particular curve looks like. But there are a bunch of models out there, these simple distributions that have these nice mathematical forms. So if f of x is always a constant, at least for some range of x, in other words, if every value in the range is equally likely, what kind of distribution is that? Do people know their statistics? That would kind of look like a hat. There would be some range of x and equal probability all the way across, and that would be a uniform distribution. Not very interesting, not a lot of variability. Another distribution that comes up all the time is where the probability of x is proportional to e to the minus x. In other words, it drops off exponentially. And so what kind of distribution is that? Be brave. Somebody say it. Yeah, it drops off exponentially, so it is the exponential distribution, which logarithmic is in the neighborhood too. All right, so if it drops off like e to the minus x, that's exponential. If it drops off like e to the minus x squared, that one has a name. That's the... Give you a hint, kind of looks like this. That is the bell curve. That is the normal distribution, aka the Gaussian distribution, things that drop off like 1 over x squared. If it drops off like x to the minus a, that's a power law. It's called a power because it's x raised to the power alpha, so it's a power law tail. Turns out power laws behave very differently from the kinds of distributions that we are used to. Dropping off like e to the minus x squared drops off very fast. As x increases, that tail is very thin. You can think of the distribution of human height, for example, is roughly Gaussian, and the tails are pretty small. There are people who are 6 feet tall. There are people who are like 4 feet tall. The tallest person ever was less than 9 feet tall. There's probably never, ever in the history of people been anybody 11 feet taller or 11 feet or taller, and probably never will be. So that's a very narrow distribution. If there were a power law, if human height behaved like a power law, I could make the same distribution so it has the same mean and the same kind of lower bound. So the lower bound for adult height is a few feet. So same mean, same lower bound. How tall do you think the tallest person in the world would be if it had a power law tail instead of a Gaussian tail? So instead of being 8 feet tall, in power law world, the tallest person in the world would be 100 kilometers tall. And I mention that just to remind you that your intuition for distributions will fail you if you are thinking like bell curves. These are not bell curves. They are very different. All right, let's get back into social.ipynb, run through the next section, which is about power law distributions, and then I'll show you a couple things up here. So the example in this section is the ZIPF distribution, which is an analytic distribution that has this property. It has a power law tail. And if you plot what that PMF looks like, if you plot the distribution, if you put it on a linear scale, where the x-axis here is, again, this would be something like the number of friends that you have. And it's on the range here from about 0 to about 7,000. If you plot it just x versus y, you can barely see any of the data because almost everybody has one friend, or whatever the lower bound is. You can shift the lower bound around. But almost everybody is right at the lower bound, and then there are a very small number of people who have lots and lots of friends. But the tail goes out to very large numbers. You can get a little bit of a better view of what it looks like if you put it on a log x scale, but where the vertical axis is still linear. At least now you can see the data, but still not very well. But an interesting thing happens if you put it on a log-log scale. So now the number of friends on the horizontal axis goes 1, 10, 100, 1,000, 10,000. And the vertical axis is probability. So 10 to the 0 would be 1. And working our way down, it's 1/10, 1/100th, 1/1000th, etc. If you plot this on a log-log scale, what you get falls roughly on a straight line. And you can see that graphically here just by experimenting and trying it out. You can also show it mathematically, which is that if f of x is proportional to x to the minus alpha, that's the definition I gave a minute ago for what a power law tail is. If that's true, and I take the log of both sides, then I'm going to get this relationship that says the log of f of x, or the log of y on the left, is going to be equal to the log of x times a constant. And that's what a line is. And in particular, the slope of that line is negative alpha. So actually, I can estimate the parameter just by computing the slope of the line. So this is a nice way to test. If you think that something might have a power law distribution, you can check whether it does by plotting it on a log-log scale and see if you get a straight line. And in the notebook, when we tried it with a ZIPF distribution, it seems like it does. We know mathematically that this distribution has a power law tail, and when we plot it, we get a straight line. Just for contrast, I also ran a Poisson distribution, which is a discrete distribution that often looks like a Gaussian bell curve. On a log-log scale, it doesn't resemble a straight line at all. At the low end, it's not straight, and then at the high end, as you get out toward high values, as you get out toward the tail, it drops off much more quickly than linearly. Okay, so a short-tailed distribution is going to drop off very steeply in this representation, and a long-tailed distribution will continue in a straight line, again representing a small number of people who have a very large number of friends. Okay, the point of all of that was to get you calibrated. So now you know when you look at a plot like this, you can tell that if you see something like this, that might be a symptom of a long tail, and if you see something like this, it is probably not. And that gets us to Barabasi and Albert, who are two researchers who studied a bunch of graphs, a bunch of networks that seem to have long tails in them. And when I say a bunch of networks, this is their paper from 1999. There are a bunch of networks. The one on the left is the actor collaboration network. So in this network, every node represents an actor, and two actors are connected to each other if they have co-starred in a movie together. You might be familiar with this graph from the Kevin Bacon game, which is the game of trying to see how many edges does it take to get from any one actor to any other actor. This is the degree distribution for the network of actors, and on a log-log scale, it has some straightness to it. They've drawn in a little dashed line there, at least for the middle part. The leftmost part looks like it doesn't quite match up. The rightmost part looks like it might drop off more steeply, but over a pretty good part of the range, it looks like it's roughly straight. The middle one is the World Wide Web as of 1999, which had, at the time, 300,000 web pages. I think there are more now.
But that also looks like a very straight line on a log-log scale. The connectivity there means that there's a link from one web page to another. And the third one is the power grid, where each node is either a generator or a distribution point, and the connections are literally connections, like wires that run from one point to another. So this is both social networks and also technological networks, engineered networks. Turns out that this is also true in many natural networks. If you look at things like protein-gene relationships, there are a lot of networks that also have these long tails. So this comes to an interesting question, which is why all of these networks have this property. So we're kind of following a two-step process here. The reason that you are unpopular is because the social network has this long tail. Now the question I want to ask is, why does the network have this long tail? And that was what the Barabasi-Albert paper started to answer. And here's what their answer looked like, is there are two essential elements. First of all, you need growth. In other words, you need a network that is growing over time by adding new nodes and new edges. If you just try to start with a static graph, and you just add and remove edges, you don't tend to get this property. You need growth. And the other thing you need is preferential attachment. That was their term. For preferential attachment means that when I add a new edge, I'm going to add new edges in proportion to the degree of the nodes. In other words, a node with high degree is more likely to get a new edge. In other words, someone with more friends is likely to make more friends. Another way to say the same thing is the rich get richer. If you have those two properties, if you have growth and preferential attachment, you tend to see tails in these distributions that look like power laws. So that's the Barabasi and Albert model. If you go back to the notebook and read the next section, which is Barabasi and Albert, you'll see what their model looks like, and we'll see some of the results. Okay, I want to come back to the slides. Think a little bit about what these results look like in terms of evaluating a model. How do we think about whether a model is doing a good job or a bad job? One of the ways to think about it is, do the data, the real world data on the left, look like the results from the model on the right. Thoughts? I mean, there are some kind of obvious ways that they both agree and don't agree. Looks better at the tail end. So the right-hand side, the real data look like they're approximately a straight line once you get out past about 10 or 20. So it's, 10 to the first power to the right of that. And the model itself certainly looks like it's exactly like a power law. The results from the model look very much like the Zipf model that we were looking at a minute ago. But yeah, for small numbers of friends, it looks like it doesn't. So this maybe describes the tail behavior, but not the bulk, the center part of the distribution. Oh. Yeah. Yeah, the question is whether this might be another example of the inspection paradox where the people on the left who have few friends are underrepresented in the sample, and that's why it's lower on the left than it is in the model. That's possible. I think their data was a kind of complete inventory of the people who were there. Oh, okay, yeah, they're not on Facebook, so the sample. Yes. But they're not on Facebook, so it's not captured in this data set. Yes, so your conjecture is that the edges that are captured on Facebook, that's not a complete inventory of all the friendships in the world. There are actual friendships in the world that aren't in this sample. That's really interesting. I would have to think about that more, but I like it. Good. Okay. Now I'm going to be a little bit skeptical about Barabasi and Albert, and I think it's good to think about this from a modeling point of view. I'll point out that this paper has been cited about 35,000 times, which is in the extreme long tail of the distribution of citations. You might know that the vast majority of papers get cited 5 times or fewer, but then there are occasional greedy people who get all the citations. And this turns out to be part of the long tail. That distribution is also a long tail distribution. So we talked about whether the data from the real world looks like the data in the model. The other thing to think about is whether the model seems realistic. Is this a good description of the way social networks are formed? In other words, do we start with a small number of people who are all friends with each other, and then each time somebody new comes along, they choose random friends in proportion to the number of friends each node has? Again, this does not seem like a realistic model of friendship in the real world. But we're coming back to the same question we had with Schelling, which is, with such a simple model, what, if anything, do we learn about the real world? What Barabasi and Albert are trying to do here is identify what are the essential features that yield power law behavior, and what are the inessential things that we can and should ignore. And their claim is that in any system that has both growth and preferential attachment, you will get power laws. And they went on in their paper to show that both of those things are necessary. If you take away growth, you don't get it. If you take away preferential attachment, you don't get it. But as soon as you have those two things, that is sufficient to produce a power law. And therefore, if you see an engineered system or a natural system that has a power law, this is at least a candidate to explain why that might occur. I said before that a lot of classical models are based on an argument by analogy, where I think that planetary orbits are ellipses because my model is detailed and realistic, and therefore I believe its predictions. And I'm claiming that these models that we've looked at today are making a different kind of argument. They're making an argument based on categorical membership. I'm saying that any system that has these essential features will have this behavior. And the work that I'm trying to do with the model is to identify the smallest set of features that are essential, the smallest set that are sufficient to produce the behavior. And this gets back to a conversation that we had during the break about whether adding more realism to Schelling's model or the Barabasi-Albert model, does that make them any better? I mean, one nice thing about complexity science, because we're working computationally, it's easy to add more realism to a model. It's easy to shovel more and more features in there, but it might not help with this argument. For this, it's kind of the other way around. You have different criteria for what makes a good model. If you are trying to make an analogy, being realistic is in some sense the critical feature, what I call the cardinal virtue. Simplicity is also good, and people will talk about the trade-offs in models between simplicity and realism. For category-based models, if what I'm trying to make is an argument like this, that says that any system in this category will have these behaviors, then simplicity, I think, is the cardinal virtue. And I'm not sure what to think about realism. I've given it a question mark, and I'll let you think about it, and we can talk about it maybe afterwards. So that's the outline. We've got through agent-based models and cellular automata and random graphs. I have a little bit of homework that I want to give you, some things that you might want to read, and then a final point of discussion. So first thing, everything we've done is based on Think Complexity, which is my book from a few years ago with O'Reilly. I'm working on the second edition now. So the code that you've been working with is all from the second edition. If you're interested in reading more, you can go to that link. That's on Green Tea Press, which is my page where I publish works in progress. And I would love it if you play with that stuff and read through the book and send comments and suggestions. It's all on GitHub, both the code and the book. So if you have thoughts, you can open an issue or send a pull request or just send me email. I'll give you some contact information in a minute. If you found the graph stuff that we just did interesting, Chapter 2 is about more graph models. In particular, Stanley Milgram did this famous experiment in the 60s looking at the number of degrees of separation in social networks, and I replicate that experiment in Chapter 2. If you were interested in cellular automata, Chapter 5 is about Wolfram's work with one-dimensional cellular automata. You can check that out. That, by the way, the picture that I have there is the one particular cellular automata, the rule 110, that is Turing complete. And I mentioned you can see that there are things that are kind of like spaceships that are moving around. And when they collide with each other, they do computations. They do things like and or gates. And once you've got that, you've got general computation. If you like the agent-based models, Chapter 9 and 10 have more about that. You saw Sugarscape in Chapter 9 in that notebook. And then there are also things like agents that move around in 3 dimensions, like Boids. These are models that try to describe herd and flock and schools of fish and things like that. And if the philosophy of science sounds like fun, you'll like Chapter 1. I sort of lay out the whole argument in Chapter 1, and then each chapter ends with a discussion of the relevant points of philosophy that have come up in the chapter. That caption, by the way, if you can't read it, says, "You want proof? I'll give you proof." What I say in Chapter 1 is this thesis, and I'll state it for you, and then I'll leave you to read about it more if you're interested. I think we're in the middle of a quiet revolution in science. And what I mean by revolution is that we are changing radically what kinds of models we think are good models, what kinds of explanations we're looking for when we ask why questions about the world, and therefore what we mean by science. Some of the things that previously would have been excluded, people would say, oh, that's an interesting toy model, you're doing mathematics, you're not doing science. Gradually, those things have become accepted. One example of that is actually Schelling's model, which when it came out, people were not very warm to it. They basically thought it was just a game and nothing interesting about the world. 30 to 50 years on, a lot of the kinds of tools that he developed, simple agent-based models, are pretty standard toolkit in economics and in other social sciences and increasingly in the natural sciences. So it's a quiet revolution in the sense that it has snuck up on us. Some of the ways that things are changing, I've already mentioned. Classical models tend to be equation-based. Complexity science uses a lot of simulation. Instead of analytic methods like mathematical proofs, we're seeing things that are like simulations. Instead of continuous mathematics like calculus, we're seeing a lot of discrete mathematics like grids and networks. And linear and nonlinear, I mentioned some of the other ways in which things are changing there. One thing that I'm continuing to think about, which is if it's true that we have a revolution in science, often science drives engineering, so what does this new kind of engineering look like? And I mentioned some of the challenges, which is engineering is relatively easy if we have isolation, we can separate things and then put them together, and if we have the ability to do optimization by hill climbing. And if you've studied some optimization, what I mean by hill climbing is if I know where I am in the design space and I know what the slope looks like locally, then I can figure out what direction to go in, and it's very likely that things will get better if I go in that direction. And if the design space is well behaved, like one big hill that has a single peak at the top, and the hillside is smooth so I can always figure out what the slope is, then it's very easy to just walk up the hill and find the global maximum. But as it starts to get rougher and rougher with lots of little deep holes and lots of very thin peaks, design in that kind of environment becomes very difficult because based on where you are, you have no idea where to go in order to get better. And even if you find something that seems like it's a local maximum, there could be another peak way over there that's much higher and almost no way to find it from where you are. This is in some sense a catastrophe for engineering because hill climbing and decomposition are pretty much the only tools we've got. Take those away and I have no idea how to do engineering in this space. On the other hand, I think there are opportunities in this space. That example is also from The Economist. I had another reference to The Economist earlier. This is one of their articles looking at parts that are designed by genetic algorithms. Genetic algorithms are a way to do search in rough landscapes. And the thing on the right there is designed by a genetic algorithm and looks very different from what a human designed under a different set of constraints. One of the things that I find striking about that is not only does it look different from how humans design, it looks very much like how nature designs. That almost looks like a knee or some other kind of joint. So that's a new kind of engineering. I think there's also a new kind of thinking that goes with this. Aristotelian logic is largely about things that are either true or false and very sharp edges between black and white and no such thing as gray. What we're finding more and more useful in fuzzy logic and in Bayesian inference is things like many-valued logics where there's true, false, and maybe, or probabilities. I think that something has a 60% chance of being true, and so on. So some other ideas there. I'll wrap up just by giving you some books that you might want to read, and then we will get out of here. I mentioned several of these, so Micro Motives and Macro Behavior is Thomas Schelling's book. Sugarscape, which you might have seen in the notebook but we didn't talk about, is in Growing Artificial Societies. And I mentioned traffic jams as one of the examples of emergent behavior. That's in Mitchell Resnick's book, Turtles, Termites, and Traffic Jams. On the topic of emergence, I gave you a link to that web page. This is also a good book by Stephen Johnson that's a nice overview of the field, written at a kind of popular science level. And then Wolfram's book about cellular automata. It's about 1,000 pages long, but it's a quick read. And then Barabasi of the Barabasi and Albert model that I mentioned has a book called Linked that's also written at a popular science level. Last thing, here are 4 ways to get in touch with me if you want to follow up. And I'll stop there. If we have questions, let's talk as a group for a few minutes, and then we can break up and talk individually. Anything we should talk about as a group? Questions, thoughts? I gave you a little bit of a brain dump there. I'm curious to see whether that sounded reasonable or crazy or you've had enough for one day. I should add GitHub to that, I've been informed. Yeah, I could do that. I could also replace Skype with Google, because that's my Google login too.
I do have a question.
Yeah.
So for the first example, I kind of understand the real world applications that are pretty obvious. Like for the game of life stuff, it seems a little more cerebral.
Mm-hmm.
Can I give some examples of like practical problems you can solve with those things?
That's a good question. So the observation is that Schelling's model seems to be about the world. It's clear that we are modeling something. Game of life seems much more abstract. It's not obvious that that's a physical model of anything. It is an example of a simple set of rules that yield surprisingly complex behavior, and that phenomenon in general applies to the world, because what it means is that often if you see a system that seems to be complex, maybe you should go looking for simple explanations. One example of that is the cone snail. Have any of you seen the patterns that appear on cone snails? Apparently these things are wildly poisonous, so don't pick one up. But if you Google cone snail and spell it right, actually, even if you spell it wrong, it still works. Thank you, Google. There are patterns on cone snails that look very much like the cellular automata that Wolfram generated in one of his early papers and in his book. And again, if you saw a pattern like that, you might initially think, that's a very complicated pattern. Maybe there's some complicated process that yields it, when in fact it's plausible that what there is a line of cells, like literal cells, that both produce pigments, and they can be in an on or off state at any point in time, and they communicate with their neighbors. And if you evolve that system forward over time as the shell grows, the pattern that you're laying out, it's sort of like a raster printer, the pattern ends up looking like that. So that's one example where a cellular automaton might actually be a physical model of something happening in the world. There are other examples. Alan Turing, of all people, proposed a model in the 1950s that used diffusion and reaction of chemicals to explain where the patterns on animal hides might come from. And what he found is a simple interaction of two chemicals that both diffuse in space and react with each other. If you tweak those parameters, you can get things that look like stripes, you can get things that look like spots, you can generate patterns that actually look like animals. And I think about 30 years after he proposed that very abstract model, people have now found the actual mechanism that produces animal patterns, and it is well described by that model. Good. Other thoughts or questions? Okay. I'm happy to stick around and talk more, but other than that, we are done. Thank you all very much. Thanks.